Good morning, still morning, everyone. So I guess all of you already see what type of the lecture you have now, yeah? So it's already introduction. It's type of combination between what you heard from yesterday and what you heard today from the Thomas. And this is kind of combination of both worlds, yeah? Okay, so this is short outline of my talk. So we first will talk about what is QMMM. So, and how you should use it, or when it could be used, or where. So, what kind of interactions you need to take into account when you're doing these schemes. So, what are these schemes? And how our current implementation of GROMACS CP2K interface is working, and maybe some examples at the end if we have time. Yeah. Okay, so first topic will be what is QMMM, why and when should we use it. So, because I'm coming actually from the biological simulations world, I'm much closer to what Helmut yesterday told you. So, and when we consider the typical biological system, yeah, it is something like protein, DNA, whatever, small molecules flying everywhere, and in the solvent, in the condensed phase, alongside with all kind of ions inside this phase. Yeah, and what it means that usually your system is quite large. And quite large here, I'm meaning that it's usually much more than even 10,000 atoms, yeah? It's usually like around 40,000 to millions of atoms, yeah, easily. And that's what you typically simulate with molecular mechanics or molecular dynamics. The problem is that some types of these systems, and especially when you have, for example, reactive systems, if you want to study reaction going on inside the proteins, which is called also enzymes, some what's biological catalyst basically, yeah, which are making all kind of things in your body. So, or maybe like in that case, it's for example of this green fluorescent protein. What it do, it just absorbs the light and re-emits it back as a fluorescent light. Yeah, it's very well known because it's also have been given Nobel Prize at some point. But the idea here is that what is responsible for this photoactivity is a very small part of this protein, which is called chromophore, like here. Yeah? And typically, this is a very small part of your system consisting of like up to several hundreds of atoms usually. Yeah? But the problem with that small part of your system is that it needs to be, it cannot be modeled classically. Why? Because, for example, like in this case, to model the spectra or absorption spectra of this protein, you need to consider electrons as quantum particles. They need to be excited, de-excited, yeah, all that kind of stuff. And this cannot be done with classical molecular mechanics. So that's why the people typically want to use quantum mechanics or such kind of systems to evaluate, for example, spectra. But still, the problem is that here you have a very small part of your system which have hundreds of atoms and which needs to be calculated quantum mechanically. But you want to consider the effect of the whole system, which is like huge, yeah, which is more than tens of thousands of atoms. So, and then the people came to the question how you can do this. So, and they came to a solution which is called multiscale approach, or in that case, it's QMMM. So basically, the idea is to combine different levels of theory and different resolutions, both in terms of dynamics, I mean time resolution, and space resolution. So, and combine them in one simulation. Yeah? So, how it has been done, how it is supposed to be done? Basically, you separate your system into two parts. One part, which is green here, it's calculated with classical force fields. Smaller part, where all interesting physics or chemistry happens, you try to calculate it with quantum mechanics, with DFT, for example. Yeah. So, like I said already, the quantum part in the small quantum systems, you can, for example, calculate for the physics properties for spectra. You can do some chemical reaction inside that when your bond starts breaking, which also cannot be explained by simple force fields. And from the MM part, what you can do is you can describe all remnants of your system, like, for example, protein, water molecules, ions, with just the classical force fields. And in that all that kind of business. There is also what you want to do. You want to do some trajectory or some, so basically you want to simulate over time your system and take the properties of it over time. Yeah. So, and how to integrate this? So there is a special mechanism which is called usually QMMM interface, which tries to combine this one and this one in order to make this one. Yeah. So, and actually already third time during the 2 days when you see this. So in 2013, there have been given Nobel Prize for development of that multiscale models, out of which you have QMMM as one of the staff, and this Ari Warshall and Michael Levitt, basically, who done this. So, yeah. The next question, when do you want to use it? Yeah. So some obvious things like reactions in solutions when your bonds start breaking or forming. Yeah, because bond breaking or forming cannot be described with the classical force fields. Enzymology, so catalysis in the biological systems. So including, for example, reaction mechanism, or in some cases, for example, the inhibition of your enzymes, or effects of the point mutations. You can do this you can use it in a structural biology, especially for example, for crystal structure refinement when you have a very exotic cofactors. Why you want to use this? Because cofactors usually are small molecules, yeah, and they are not parameterized in your force fields. So you either need to do pre-parameterization, or you can just use QMMM, because in QM you can put your cofactor as QM atoms, yeah, and basically you have intrinsic parameterization of them on the QM level. Second is kind of following from the third point. Yeah, his first point is ligand-protein interaction. Yeah, for example, you have your protein to which bond some small molecule, and you want to, for example, calculate binding energy, or you want to calculate, you want to evaluate interactions between the molecule, ligand, and the protein. And here, either you need again to parameterize your ligand first to use it in the classical force field, but maybe your ligand at some point will start to, instead of interactions, then it first can react with your protein or inside your protein, and then the bond breaking again occurs, and then you will need to use QM. And of course, the photobiology or photochemistry in general, when you have your system on the excited state. Yeah, so when you want to calculate absorption spectra, emission spectra, excited state dynamics, all that kind of stuff. Okay. So there is a link where you can see there was a virtual workshop a couple of years ago where all kind of these use cases was described. So there is a link to this. Okay, so now let's see what the kind of interactions you would need to describe in order to make this QMMM interface happen. So as I said already, we have this kind of hybrid scheme when we have a small part is QM, the rest is calculated with MM force field. So, and then we will have three types of interactions, what we could expect on a highest level. So we have interaction between particles in QM region. Yeah, we have interactions between the atoms in the MM region, and then we have some interaction between QM and MM. So for the first two, it's pretty straightforward. On the MM force field level, on the MM level, like for example in GROMACS, you describe this by the two terms, so bonded, non-bonded. So bonded interactions, it's usually a very simple functions which include two atom interactions, like bonds between two atom springs, basically. You have the three particle interaction, which is angles, so it's basically like bending of the angle. You have four particle interactions, like torsions. There can be several types of them. Yeah, but it's basically you have four atoms, and they just also can flip here and there. And you have also non-bonded interactions. They usually include two terms. First is van der Waals term, or Lennard-Jones interaction, through the Lennard-Jones potential. So it's R12, R6 potential. And it's usually defined per atom type, so for oxygen, hydrogen, carbon, and so on. And then you will also have these Coulombic interactions between the partial charges of atoms assigned by the force field. Yeah, is attraction and repulsion. Okay, and all of this, why it's called force field, because there is a lot of constants, like case here, 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 partial charges, coefficients of the Lennard-Jones interactions. They are all predefined in the tables for each atom type, or for bonds, for example, it's for each pair of atom types, yeah, and so on. And this is called force field. So you have a lot of the parameters with which you describe your system. So other type of interactions is QM interaction within QM system, yeah. And for example, in CP2K, like in the previous lecture was shown, you are trying to describe this using the density functional theory, using this mixed Gaussian plane waves approach, yeah, GPV. And here where you need to solve that Kohn-Sham equations, what have been explained in the previous lecture. So, and after the solution of Kohn-Sham equation, you will get energies and forces and properties of your QM system. Yeah. Okay. Now the third, you of course have also the third type, and this is interaction with how you organize the interaction between your QM and the MEM subsystems. And this is what makes the QM interface very special. So first of all, you would need to understand that there is several types of approaches which you can take to achieve this here. First, and very old one, which is used in the 80s usually, so which is called mechanical embedding. What it is in the essence that the total energy or total energy of your QMMM system like this is calculated as total energy of your system at the MM level, including that QM atoms. So everything here is calculated at the MM level. Then you add here just the energy of QM system in a vacuum without any external MM interaction, yeah. And then you subtract the energy and forces also from the QM atoms on the MM level. So basically you take the whole molecular mechanics simulation system, you cut from it on the molecular mechanics level your QM part, yeah, and you add into it at the QM level. So that's why it's called mechanical embedding, or it's usually called also subtractive scheme, because you subtract your QM system from your total MM system. So what is drawbacks of this? The main drawback is that the interaction between QM and the MEM system in that scheme is purely molecular mechanical. Yeah? So your interaction comes into this term. So basically it means that your QM system, as I said, is calculated in the vacuum. So QM system does not know anything about MM system around. Yeah? And interaction between QM and the MEM system are going through this molecular mechanical force field. So a drawback basically is that you still need to know at least partial charges and van der Waals interactions, non-bonded basically terms, of your MM system, or of your QM system in the MM force field. So, and you're losing the advantage of QM-MM of having be agnostic to the force field parameters. Yeah? But it's very simple. So in order to overcome this, there is a second type of embedding, which is called electrostatic embedding. And this is usually defined as when your QM system feels the polarization due to point charges from your MM system. And this is usually called additive scheme because how it's calculated, you take, instead of taking the whole system at the MM level, you only calculate MM system without the QM atoms on the MM level. And then you add QM system calculated in a field of partial charges of MM system. So your MM system or your DFT, Kohn-Sham DFT, should have an additional potential due to external charges predefined by the molecular mechanical force field on your electrons inside the Kohn-Sham equation. And there is a third type, which is not really widespread up to date, which is called polarized embedding. And polarized means here that it's the same as electrostatic embedding, plus your MM point charges could be also polarized by the QM electron density, meaning that your MM atoms will point charges will respond to the QM density. For example, if you know there is such a polarizable force fields like amoeba, for example, which can have additional terms, electrostatic terms, polarization terms called, yeah, which can slightly change your charges by external field. It's not very well spread and widely used up to date, but just in case there is also such type of things. Okay, so this is abstracted scheme. I probably already explained to you. Yeah, so it's done in 3 steps. And this is, again, the advantages. Yeah, so you don't, your QM and MM parts are basically decoupled. You need to just run MM and QM separately. So, but the main cons is that, yeah, you need a force field for your QM part, which is usually want to avoid when you do QM. And the force field either needs to be flexible or there should not be any chemical bond breaking forming happens. Yeah. And your QM part also does not feel that polarization of the MM part. For the additive scheme or electrostatic embedding, the situation is more advanced. So this term you calculate from Concham DFT. This term you calculate from the force field, and this you typically calculate by the, again, 2 terms, bonded, non-bonded. The bonded thing is calculated basically, you need to calculate them only if you have a bond breaking between the QM and the MM part, yeah, because you break the bond on the boundary between the systems. And non-bonded are also, in that case, takes into account 2 parts. So first part is again sterical Lennard-Jones interactions between your QM atoms and the MM atoms, and electrostatic interaction. So typically this, as I said, so this and this are still taken from the force field, because Lennard-Jones parameters, they are more or less the same for all kind of atoms. They are just depend on the atom type, so carbon, hydrogen, oxygen, and so on. So you can just safely take them from the force field. Bonded interactions you only need for the at the boundary. So you need only to know what is the force constant of the bond when your breakage between the QM and the MM part happens. And this is much more easy to parameterize. And the electrostatic term is basically here what is called the interaction between QM density, electron density, and the MM point charges. So how it's calculated, usually when you have this also breaking of the bonds here, for example, you're breaking bond here and you're breaking bond there. So you also need to somehow close the your wave function, because what happens here that if you break that bond, it happens that your atom in QM system, like this, for example, carbon, it no longer have its counterpart here. So it needs to somehow, but there should be still an electronic orbital which is pointing towards that atom. So, and you need to solve that problem. How to solve them? There is at least three options how you can do this. And usually, in most cases, QMM does the first one. So basically what you do, you add additional hydrogen atom on the side of this broken bond. So basically here. Oops. Yeah. So basically you add here the additional hydrogen atom, also called link atom. It's completely fake atom, so it does not exist in reality. What it just do, it just tries to keep your electron density in the direction of the bond correct. Yeah. So it just form it somewhere on the bond. It's usually connected to the bond here. So the red point here is this link atom, basically. It usually resides somewhere in the middle of the bond, and forces from that atom are redistributed to the QM and the MM atom on the bond. Yeah. Okay. There is other options how you can do this. You can use again pseudo potentials. So basically the pseudo potential on that atom with the broken bond, so on that QM atom, which will enforce additional electronic density here on the bond. Or you can use the additional frozen orbitals or frozen hybrid orbitals on this bond. Basically, it's the same, but here you use pseudo-potential, here you use the frozen orbital, which directs along this bond again. But in most cases, the most simplest approach is using these link atoms, and that's what the people are using. Yes, okay. So these coupling approaches, so in mechanical embedding, as I said, you don't have, your QM system doesn't know anything about the MM systems. In the, yeah, so in electrostatic embedding, they're filling both. Polarized embedding, they are self-consistently influence each other. So because in CP2K and GROM CP2K we primarily use the electrostatic embedding, I will talk more about this. And so then the electrostatic embedding implies that your electrostatic interactions between your QM and the MM atom subsystems are handled during the Kohn-Sham solving of the Kohn-Sham equation. Yeah? And how it's done? So basically, your MM atoms or point charges on your MM atoms, they are interacting with all electrons in your system, or in case of Kohn-Sham, like again from the previous lecture, they're interacting with the electron density, your Kohn-Sham electron density. And this is a very simple, actually, integral. The only problem here is that you need to calculate this sum over all interactions for all MM atoms, which could be millions. Yeah. And you also need to take into account the second thing, and the second thing is your system in GROMACS, and in most cases, in biological simulators, it's 3D periodic. Yeah? So you have a 3D periodic system. So you first need to calculate this from all MM atoms. Second, you need to take into account that periodicity. Okay. Yeah. So basically, short-range part, which is represented here, it also have other problems. I will show next slide, which is called electron spill-out. And the long range, if you do it exactly, yeah, or if you want to do it with these exact methods like eval summation, for example, for the periodic systems, it is really huge in cost. So it can eat the whole advantage of using QMMM just because of this. So first problem is short-range interactions, short-range part of your interactions, QMM interactions, and this is called electron spill-out. And it is very easy, could be understood on the very simple picture. So for example, you have here your QM atom with some electrons around it. So you have your QM density. And here, suddenly, your electrons start to feeling high positive charge nearby to the electron density, to where they reside. What will happen to that electrons, guess? Yes, they will try to form blob here. Yeah? So basically, because your Coulombic interaction, it just have this, how it's called, asymptotic wrong. It's if your distance to your point charge is low enough, your energy starts to become almost infinite. Yeah. So your electrons will try to go to this field with a very high energy when they're really happy here. So and electrons try to escape your QM region and tries to form a blob somewhere here, which is not a good idea. Yeah, usually because it doesn't happen like this. If both of these atoms would be QM, you will probably form some bond, or your electrons will feel also electrons of this atom. They will repel each other, yeah. But here, just because it's only you have a charge, they will try to form electron cloud around that charge. So, and especially these artifacts is very visible if you use large basis sets. For example, if you go to the augmented triple zeta basis set, you will immediately start to see these blobs of, and then you do QMM calculation, and then you try to render your HOMA orbital, and that HOMA orbital will suddenly have a blobs of this density on the nearby MM atoms. This is actually this electron spill-out effect. How you can solve this, and how it is solved nowadays, and also in CP2K, that instead of point charges in MM region, you use the smeared density. So you smear your charge, you're making Gaussian out of your charge. Yeah? So it's not point charge anymore, it's just a Gaussian with some half widths determined by this smearing parameter, and by N-Heights, our total integral of this is defined by the MM point charge. Yeah? So now your electrons will interact not with the single point charge, but it interacts with Gaussian. And with Gaussian, it does not have this huge problem with increasing up to infinity the energy, interaction energy. So, and this is usually how done smearing. They're using these so-called error functions, which is just integral of the Gaussian whatever. Yeah. So you use this as a smearing function in CP2K. And then, yeah, that's what I wanted to say. So if you have a point charge, which is blue curve here, so the blue curve is interaction with a point charge. It just goes to infinity when your distance between your electron density point with this point charge becomes too small. It will go to infinity. But the good point about this kind of smearing scheme is that it has a finite. Yeah? So we will never go to the infinity. And the second, of course, point is that you want to also calculate the long-range interaction. And the long-range interaction for when you start to calculating this total interaction, so you need to evaluate the whole integral of the whole atoms, as I already said to you. And the direct evaluation on the grids or multi-grids, which CP2K is using, it have a really huge number of individual points you need to evaluate. Yeah. So because your grid have number of points, you have number of charges, and usually grids is quite dense, so you have really huge number of operations you will need to do. So you need to somehow avoid this. And idea would be that, of course, your QM region here is grid, and here is your electron density, and here is your charges which is around it. And in order to avoid this in CP2K, kind of a very long time ago, it was proposed this Gaussian expansion of the electrostatic potential approach. So what it is doing, it is trying to approximate this smeared point charge potential, not point charge, but point charge potential. So it means that electrostatic potential due to this smeared point charge. It tries to approximate it as a sum of several Gaussians, like here, Gaussian potentials, plus some remnant function, which have been proven in the paper that it is really smooth, so it doesn't have any sudden, any sudden behavior. It's just a very smooth function. And then what it has been done for each point charge, you do this kind of expansion, which can be calculated analytically. And number of Gaussians is the only parameter, but it's typically between 4 and 12 Gaussians per one charge. And then what you do, you have now these n Gaussians, and you just could project them onto the same multigrids on the which you are using to project the normal basis functions. So what you do, you can reuse this CP2K Gaussian plane wave idea also to the point charge. But instead of point charge, you project directly the interaction potential. Basically, now each of your points onto which you calculate your electron density also have, in each of these grids, in each of these points of the grids, you also have the potential, electrostatic potential due to external point charges summed up in each of these grid points by projection as the sum of the Gaussian, basically sum of some Gaussians, which you anyway do when you calculate the electron density, and plus some very smooth function which can be projected on the coarsest level grid. This one, low, you just calculate on the coarsest level grid because it's very smooth. So, and this speed ups the whole calculation significantly, like orders of magnitude. And then you project this onto the real space multigrids. So how it's done is explained here. So for example, you have, let's say you have a point charge, and you have 3 Gaussians, which is, 2 Gaussians plus 1 long remnant function. So, and for example, you have 2 point charges. One is located here, one is located there. Yeah. So the first electrostatic potential, or the first Gaussian, for this point charge, it is kind of localized. and this is projected onto the grid level, let's say 0 level, yeah, the finest grid. This one does not project onto this grid at all because it does not overlap with this grid. Yeah. So for the second Gaussian, you see that it can be projected already for this point charge, for yellow one. So this point charge, it can be projected onto the more coarse grid. How it's determined onto which grid is projected is also explained by Thomas in previous lecture. So it basically by a number of points that Gaussian covers on the grid. Yeah. The CP2K always try to allocate or project your Gaussian function onto the grid, onto the coarsest possible grid, which describes your Gaussian with some number of points. I forgot, it's like 20 or something like that. So you can actually change this in the CP2K parameters. And and also on this level, your second point charges have some overlap with it, so it also projects onto this grid. And the remnant parts that are low here, it is projected onto the coarsest grid, but onto all points of this coarsest grid, basically, just a very long range. Okay. Yes. Okay. Also, the main one of the features of the GROMACS CP2K interface, CP2K feature, that how the periodic QMM system is treated. And this is not really trivial. It is done in this paper, and this is working like this. So first, you have your QM system, you have your MM system, yeah? They have, both of them have their individual boxes, three-dimensional periodic boxes associated to them. Usually, MM box is much bigger than QM box, yeah, because you want to localize your QM into smaller space. So, and how the approach, the fully periodic QM approach works in CP2K, that it's first do this G projection of the potential. So it basically wraps your whole MM system onto the QM multigrid. Yeah. Then next step, what actually CP2K calculates with GPV, it calculates this system. So it just replicates your QM system with G potential in 3D and calculates this three-dimensional system like this, which is not the same system as it was initially, as you might see. So, and then you need to do some correction. And how this correction is done? So it's need to account for the correct periodicity of your QM system, and they then use a Blochel scheme, which restores which basically splits your quantum systems apart from each other into the correct periodicity of your MM box. And this scheme uses this decoupling and recoupling of the electron density in multiple expansion. So basically what it do, it takes your grid density, it calculates the multiple expansion of the density on the grid, on the coarsest grid, and then it just calculates, it just unbinds this system from all others by using these multiples. And then it shifts the system to the correct place in space and calculate back the recoupling. So it basically reduces the total interaction energy by a factor of this periodicity. So that's basically how it's done in CP2K. And the next, the next section will be about GROMACS CP2K interface. So how to combine GROMACS MM force field with MM simulation with CP2K and QM. So, and as I already said, so we have CP2K, which can use quick step with mixed Gaussian plane waves approach as a density functional theory, and GIP as the coupling, QMM coupling. And you have the GROMACS, which have a force field, which need to calculate interactions between the MM particles. And GROMACS is also very well for doing the classical MD and all kind of approaches, sampling approaches, for example, from GROMACS is very well developed in GROMACS. Okay, and what we have in that interface, that it is automatically for you, it can convert topology from GROMACS MM simulation or GROMACS MD simulation to the QMMM. We have some pre-validated QM parameter setup, but actually I would say that they're overkill meaning that they are much better than they could be used, just in case that the simulation will be more stable. So by default, your parameters will be just more robust probably than you need. And of course, it's compatible with GROMACS simulation techniques, and it's compatible with third-party software analysis, which can take GROMACS trajectories as the input, GROMACS trajectories analysis. So let's start with the first house automatic. What you need to change in your topology of your MM system in order to make it QMM. So, and there is like 6 points. So you need to first remove partial charge from your QM atoms, so your MM atoms will no longer know anything about your QM atoms, point charges. So you need to remove Lennard-Jones interaction between QM and QM atoms, between that yellow atoms, but you need to keep the Lennard-Jones interaction between yellow and black atoms here still. Yeah? Then you remove all bonds which are connecting to QM atoms, it's that yellow atoms here. You keep the bonds which are connecting black and yellow atom. So you remove only this yellow. So you remove angles which contains 2 or more QM atoms, meaning that this, for example, angle is removed, and these all angles are removed. But for example, this angle, 2 black atoms and 1 yellow atoms will be kept. Then you need to remove dihedrals containing 3 or more QM atoms. Yeah, so it means that, for example, this one is kept, but like black, yellow. But this black, yellow is removed. So, and of course, you need to clean up any constraints, additional constraints, or constraints on QM atoms. For example, for QM waters, you use these settle constraints to keep the waters rigid. You also would need to remove them for the QM sim if the water is in the QM subsystem. Okay, and of course, you would need to also generate CP2K input and include that additional link atoms into CP2K input here. And that's what the interface is doing. So how it's typically working. So you, as yesterday, you set up your system exactly in the same way. Yeah. So you can take it from PDB or from whatever database. You need to make topology. You can do this, all of these simulations you done yesterday with it, yeah, if you have all 4 sweep parameters. And in order to switch it to the QMM setup, you just need to provide the several options in the MTP files, and you need, in the index file, mark up a group of atoms which will be your QM atoms. That's all you need to do to start with it. And as an additional point, the interface can generate for you QM input for CP2K, but you can also use your own CP2K input. Yeah? As I said, because the default parameters are kind of overkill in terms of stability of simulation. How it's working on the lowest level, in the GROMACS, if you want to understand more about coding, especially considering that the GROMACS is C++ code and CP2K is Fortran code. But so it's kind of already not really easy. But the thing is that this is a typical MD flow. Yeah? So how your MD program works, GROMACS as well. So when the QMM interface takes place is this part. So when you calculate energies and forces of your atoms, in the GROMACS we have a unified MD modules framework with which anyone actually could implement any forces they want into GROMACS as an additional forces, which GROMACS will take into account, energies and forces. And there is a special part of these MD modules, or implementation of it, it's QMM MD module, which interacts with CP2K. And CP2K in that case, it is really linked into the GROMACS. Yeah? So the CP2K and GROMACS is with that interface is just one package, one huge executable file, I would say. And then internally it calls the coordinates. That QMM module, it takes care of initializing CP2K, passing it system, coordinates, all that kind of stuff, setting up, and then set the coordinates, box dimensions, everything, and asks the CP2K to calculate energies and forces and provide it back to the GROMACS. And then the GROMACS can do the, and then the GROMACS can do this integration of trajectory. Okay, then is there some questions about the general, how the interface is working? Yep.
You don't need, if you do QMMM, you don't need the force field parameters for the atoms that are fully inside your QM system, but you do need them for the ones bonded to your MM system.
Yes, you need still bonded parameters. Also, so maybe let me be clear, you can also skip these steps. You can just directly go to QMMM, yeah? Especially if you don't have any parameters of your, for your ligand or whatever, yeah, in the MM. It's not suggested that it's the best approach, but, but you can do this potentially, yeah? But if your system includes this bond breaking, usually, yeah, you cannot avoid this because, yeah, as I said, so this bond at least need to have some parameter. This angle needs to have some parameter so that the relatively your QM system will not drift into MM system. Yeah. Yeah, this kind of stuff. Yeah.
Can water diffuse in or outward the QM region?
Yes, that's one of the potential problems I foresee for your simulation. That what could happen, especially if your system includes the water molecules, yeah, it can diffuse in and out. And this needs to be checked. That's why usually it is suggested that the all waters which are not directly participate in, for example, reaction, they should be MM waters. Because for MM waters, if MM waters will diffuse into the QM system, it is not a problem. It is just solved by this smearing potential and jib. But if your QM water will try to leave the QM box, your simulation will crash. Okay. And this is often seen in the, especially in the enzymology simulations. I will show you one example where it potentially could happen. So that's why you need to be sure that your QM water will not leave the QM box. So it should be either bound. So if you want to, for example, explore the enzymatic reaction, which includes the water attack, for example, on phosphate or whatever, you would need to keep this water always nearby your phosphate via the, for example, additional, not bond, but some harmonic potential, yeah, whatever, so that it will not leave the QM box.
So that means I can extend the simulation time if I use some other external potentials that keeps the water close.
Yes. Water is something you need to consider, yeah. Okay. But in general, if your water does not participate in any reaction or any process, just keep it MM, and then there will be no problem. Yeah.
So how would you apply this if you have like a metal oxide surface and you want to simulate the waters close to the surface in the QM way, but the ones further away with MM? How would you do this that they don't switch?
Yes. So for now, the interface doesn't allow you to do this. You would need to predefine which atoms is QM and which is MM. This is a limitation. So as I said, really think twice whether you need to make your water quantum.
So you can only do this if the QM waters are quite strongly bound.
Quite strongly bound first, or you need to bind them by the additional harmonic, let's say, potential. Yeah. So you can keep them very easily near the surface if you just apply. In GROMACS there is also possible. Yeah, you can, for some part of your system, you can do additional, they call pulling force towards, for example, your surface. Yeah, which is predefined, for example, by this some z coordinate, and you can force to pull them towards the z coordinate. Yeah, it can be a very small force, of course, but still, yeah. And there is a third problem which I did not discuss in the lecture, that your actually it's very funny property again of the QMMM, and it's actually very funny property of the Conchem and any SCF wave function method, that the your QM system very likes to be in the point charges. So it means that if you have, can I plot here? No? So I just did not put this because it's a very specialized question, but the idea is that, for example, if you have your water molecule, which is QM here, yeah, it likes to be inside the waters. It tries to surround herself in the waters, yeah, rather than be close to some QM part. So the QM part, if you, if you just put it into the water, and if QM parts, for example, consist of 2 or 3 molecules, what will happen? They will try to move away. Why it's so? Because the electrostatic interaction with the point charges or with the classical charges is stronger than the interactions between the QM electrons. It can be very simply understood because with the point charges have only electrostatic interaction, like attraction, yeah, or yeah, mostly attraction, yeah, in that case. But the thing is, between QM, the electron density, you also have exchange interaction and correlation interaction, which weakens the Coulombic actually potential. So, and of course, the QM will try to run into the That's why, again, if you have QM water, it's better to keep it in the QM system by some additional restraint or whatever. It will anyway will try to live to the Maybe
a follow-up question, if it's allowed. Is there any development on an adaptive scheme in CP2K-GROMACS?
There is adaptive QM, which allows you. There is not in GROMACS CP2K, in pure CP2K they have this kind of adaptive scheme when your QM system is adapting towards current situation. So your QM system could change throughout the simulation. The problem is that all that schemes, as I see for now, they are not energy conservative. Of course, yeah. For example, if suddenly your water molecule switches, yeah, so it means that you switch one water molecule with other. At some point, it will just break your energy surface and gradients. Yeah, so it will be non-energy conservative anymore. Yeah, but there is such schemes available, especially for the water molecules exchange, as you said. Like,
but this effect is true for all QM particles and not only for water.
Yeah. This is one of the problems. So if you have several molecules in QM region, beware. They need to be kept together because, or else the water will just split them quite fast. And again, they will just leave your QM box and the simulation will crash. Yeah. Okay, so yeah.
I have a question about the QM part. If you have like a charged species in there, do you then do like implicit solvent? Because
again?
If you have like something charged in the QM part, like for example an H+, do you then use implicit solvent or really the gas phase? Because I can imagine that the forces are maybe.
So if your QM system is charged, yeah, then it means that when you do this topology preprocessing step, so it's completely fine to have a charged QM system, yeah? No problem at all. Even today in the exercises, in the hands-on session, we will have such system. And the thing is that it needs to be compensated such that your total charge of your total QM plus system is kept as 0. Yeah? So you don't need any additional solvatation models like implicit solvent or whatever, as long as your total charge does not change during the transformation from or MD to QM. The thing is, even if your charge is changed, so even if you have non-zero total charge of your system, the interface will still run. It will just warn you. And how then it's added into the total, and how it affects the total energy, that there is actually, if you check the eval summation scheme, or PME or whatever, eval or particle mesh eval, then there is a zero term, which is just a total charge of your system. So it can be done, but how it's usually imagined that your system is now, you put your system charge, like for example, we have total charge of system +1, yeah? How the GROMACS considers this, that this is +1 system embedded into the uniformly distributed electronic gas with a -1 charge over the whole system, yeah? So it just compensates like this. So it's a well-known problem, especially, for example, if you have system membrane for biology. For example, if you have membrane system, you have membrane protein between two solvents, then you have membrane, and then you have other water. Yeah? Then if you does not neutralize your system, what will happen that even your charged molecules will try to penetrate into the membrane because there will be higher electrostatic potential, which is not true. And for such system, if you have a phase transition in your system like this, so water, membrane, water, then you should really neutralize the system. If you have a system like water-soluble protein inside the water with some ions, yeah, it's usually not a problem. Even how you can check this, you can just scale up a bit, change a bit charges of your ions inside your water, like sodium ions or chlorine ions, by a very small fraction, and neutralize your system. Yeah, it's actually it solves exactly the same as it solves in GROMACS. Yeah, so it's nothing special about this. So, other questions? Okay, if no, then I will maybe, how much time do we have? Like 15 minutes? Yeah, sure. Yeah, okay. So let's do some use cases or what you can do. So this is actually how your simple QMM calculation will look like in the GROMACS CP2K interface. Everything you need to do after the classical MD or after you have some GROMACS topology, you just specify these 4 or 5 additional parameters in the GROMACS MDP file. Yeah. This first parameter is just activate, instructs to activate interface. Yeah. Then all other parameters will be active. So this QM group is a group from the index file in which you define the numbers, indexes of your QM atoms. Then there is a method. So by default, the method is chosen to be PBE, which is actually PBE in the double zeta mol-opt basis set, actually with D3 potential. So it's PBE D3. Yeah? It is dispersion correction. Then you need to also specify the QM charge of your system and its total charge of your QM system. That's actually to your question. And you, of course, need to also supply the multiplicity. Yeah, usually it's singlet for the biology systems. Okay. Then you will have the normal GROMACS. You will have topology TPR file with your system prepared. And actually, CP2K input file will be encapsulated into that topology file. And once you run md-run, they will appear in your directory. So once you start md-run, it will unpack it from the TPR file and put it into the directory with the TPR. Okay. This is how pre-generated CP2K file looks like. So it's several sections in it. So this is just a header. Then the main is for cval, and the method here is set to QMMM. It's meaning usually quick step plus zip. Yeah, so it instructs that the following will have both QM part and the MEM part. Then there is grid setup and DFT setup. You can check during the hands-on how it looks like. But as I said, the basis and plane waves and multigrids just here done with a bit of overkill. So just to ensure more stability of the simulation. So for QMMM, what you need to set up is you need to set up dimensions of your QM box and the MEM box. So you need to set up the JIP, and not you, but what the interface will do. Yeah, it will set up the JIP, Blöchel decoupling scheme, and link atoms here. So in the MEM, what is done here, it just basically you will see this is just switch off all interactions between MM and the MEM, between point charges. For a very simple reason, this is calculated by GROMACS. Yeah, so the CP2K does not need to calculate this. By default, it will, but you need to switch. That's why it's switching it off. And here it's Gaussian basis sets and atoms as here. And also here it links to the PDB file with initial coordinates for your system. Okay, and this is how that PDB file looks like. So it just split into two parts, QM and MM. And for QM part, your point charges is 0, and for MM part, point charges is put into this external additional field in the PDB file here at the end of the string. Okay, so this is how, for example system I've took here is just JSP chromophore, yeah, which is called HBDI. I showed you previously, so it's just some chromophore with in the box of these tip 3p waters, and again, so it's actually the total charge of this chromophore in water is -1, yeah, for example. So there is also sodium counter ion in the box. Okay. So and here it's energy minimization of this. So in QMM setup, yeah. So it's not MM, just QMM. And if you do NVE simulation, so we want to be sure that the energy conservation holds in some, like, you know, in the time, and across the this like 10 to 12 picoseconds, it seems like it's stable more or less, with fluctuations around 2 kilojoules per mole, which is usually connected to this effect what the Thomas tried to explain with this ripple effect of the because your grids are sensitive to where your atoms is actually, yeah, with respect to them. Okay, so there is also possible to do pressure and temperature coupling. So there is a thermostat and barostat. For barostat, actually here I strongly suggest to use instead of Berenson, which was previously used. Now there is a much better barostat, which is called CP2K in the GROMACS. It's a newer version of GROMACS from 2022, I guess, GROMACS 2022. It's really suggested to use that. It's much better do a barostat. It's much better barostat. Okay. And with this setup and on one 128 core node, with 1 femtosecond time step, I have like 10,000 steps per day easily on this with a GROMACS CP2K interface. Okay, let's go to more interesting step when you have these simulations of the proteins. And first is just simulations of the reaction. So what happens in that reaction? So there is a big protein. There is a very small part of it with cofactor here, which is a very big molecule. And what reaction could happen here? It happens with isomerization. So this ring, it can flip down, basically, do it like this. Yeah. Flip. So, and for that, we used umbrella sampling. So how many people of you know what umbrella sampling is? Could you raise your hand? Okay, so not all of you. I will firstly explain for the other people, yeah, what it is. So basically, when you want to calculate free energy of your reaction, yeah, it's Gibbs energy or Helmholtz energy, whatever. So of course you need to from state A, let's say, to state B, yeah. And you want to do this because you want to calculate free energy. You also need to take into account some entropic factor. So you need to take into account dynamics of your system. So what you can do, you can pull the system in the dynamics, yeah, with some force from state A to state B. Yeah. But the problem is that typically if you do it like this, you would need to do this many times from A to B and from B to A. So and then you can average force, or not force, but average the work which your pulling force done from A to B and from B to A. As thus you can extract from these pooling simulations, you can extract the free energy or partition function, what the previously Thomas tried to explain. From that you can extract it. The only problem is that you need to do that pooling really slow. So you need to do it really, really slow, and the force should be really small in order for system to be in the in order to keep ergodicity of your simulation. Instead of this, what the people decided to do, they decided instead of pulling through the whole coordinate in one go, they decided that they can do that pulling in a very small steps. which is called umbrella windows. Why it's umbrellas? Because I will show you. Yeah, because of this, so it looks like, if you especially cover it, it looks like umbrella. So, and what they do, they just define multiple umbrella windows, in which of these umbrella windows you apply just a normal harmonic potential, such that your system could only deviate a bit out of this equilibrium value. Yeah? And then you can do these simulations with that external harmonic potential in each of these windows along the reaction coordinate. Take the distributions of your coordinate in presence of this external harmonic potential, so they will look something like this. And there is a formal proof that then out of this overlap between these windows, so these overlaps areas, you can actually calculate the free energy. You can calculate partition function, and you can calculate free energy difference between the final state and initial state. And this is done with, in GROMACS, you can do this with GMX Ham tool. So in that case, it looks like this. So this is each individual point is an individual window you calculate. And each of these windows was simulated like for 20 to 30 picoseconds. Yeah? And out of this, you can build a whole profile, which is very nicely showing you the free energy. So this starting point, this is end point, and this is transition state. So it's very nicely converging profile. So as a case, so it's RNA-dependent RNA polymerase of SARS-CoV-2. Maybe it's not really interesting anymore for the people, but just in case, because this is actually the system where the water molecules are important. So what it's doing, it's responsible for the replication of the viral RNA, and basically it takes the one RNA strand of the virus, and it is trying to build the double helical RNA out of it by combining the other nucleotides to the growing strand. And here what happens that in the process of the simulation, so basically your this is ATP molecule initially, so like here it's ATP, and it's slowly attaching to the previous nucleotide like this, and the diphosphate it just forms and leaves out. So in reality there is also water molecule here, which is not shown, which interacts with this phosphate. So, and that water molecule needs to be kept in the QM region, and here in that simulation I've done this by using this additional harmonic restraint, so that it will not leave the QM region. Okay. So how this reaction is defined? So you have your two distances, like D1 and D2. Yeah. And we want to perform the free energy simulation of this reaction coordinate, which is D1 minus D2. It's pretty standard, I would say, reaction coordinate for these phosphotransfer reactions. And this QM subsystem, WM subsystem setup. So, and this is what we have. We also compared this between GROMACS CP2K and just pure CP2K simulation, yeah, without the GROMACS. The same umbrella windows, the same everything. And as you can see, yeah, the results are almost identical for both of them. So I would say that there is no much difference what to use. The only thing that in GROMACS you have this topology, easier topology setup and everything else. And this is what you have when you convolve the profile. So there is some difference in products, but also like sub kilojoule per mole, something like this. Okay, what's good about the GROMACS that you can even do this in two-dimensional space. Yeah. So instead of using this one reaction coordinate, you can use two reaction coordinates at the same time, so both D1 and D2, and do a scan of the two-dimensional surface. This more advanced method, which is called accelerated weight histogram method. You can read about this in the GROMACS papers. So it allows to do this multi-coordinate. And if you see that there is, again, products and reagents, so the reaction goes like this, on this black line. And if you check this black line, this is exactly the line which defines this D1 minus D2 reaction coordinate. So it also confirms here. So that the lowest energy pathway is going through this D1 minus D2 reaction coordinate. Yeah, so you can do something even like this. And some advances, so like already Thomas suggested, so about some suggestions about the CP2K parameters. For biological systems, we have this guide, how to choose on this website. You can read how to choose, for example, basis set and how to choose cutoffs, how to do this small stuff. Yeah? And some additional papers about, not paper, but additional articles or pages on how to understand CP2K output, how to do maybe a simplest troubleshooting of your simulation and all that kind of things. So please feel free to read this as well. Some acknowledgements. Also, for your consideration, you always can go to this BioXL forum and ask questions about GROMACS, about GROMACS CP2K, about other software packages used for modeling of the biological systems here. Yeah, so thanks for your attention. Some questions? Yeah.
How do you do umbrella sampling with CP2K? How do you do umbrella sampling with CP2K? Just
Plant. We use plant.
it's in GROMACS, yeah?
In GROMACS, you can do it with the GROMACS itself, or you can do it with here for comparison. I use plant in both cases, just for comparison. But in GROMACS, you can do umbrella sampling by its own. Yeah, not a problem.
I just wanted to double check. So the smear charges are only for the QMMM interactions. They're not for the MMMM
Wait.
interactions.
Yes, you are correct.
Okay.
So MMM interactions are calculated by GROMACS via the PME procedure.
Yeah.
So it's used particle to mesh yield. So it also has this splitting called the with-error function. Yeah. But about smearing, yeah, actually strictly saying, GROMACS also do smearing.
Oh, okay.
Actually, yeah, not really. So it have two components. So short-range components GROMACS calculate exactly without the smearing. But for long-range component, what it is doing, it is do PME procedure, and what PME is doing, it smear your charges onto the grid. Right. You interpolate your charge or smear it onto the grid. Then you calculate long-range interaction on that grid. Long range meaning that with respect to the also periodic boundary conditions, yeah? And then you add that component into the total energy. So strictly speaking, I would say GROMACS also is smearing, yeah. Yeah. Yeah.
Sorry. Thank you for your nice talk. Just I didn't realize what does that mean when you talk about adding some flexibility for the advanced user.
Yeah. It will be shown in the hands-on section. So in reality, you can provide your own CP2K input to the GROMACS. Instead of pre-generated, which, as I said, it just overkill in the stability, you can reduce, for example, grid cutoffs to a more meaningful value. You can decrease, for example, precision if you do molecular dynamics, because for molecular dynamics, typically you don't need precision up to the 7th or 8th digit in density. Yeah, so all that kind of things. And then you can provide it to the GROMACS, and the GROMACS will digest it, hopefully. I would anyway suggest you to start from the pre-generated input. So you just basically take what the GROMACS CP2K interface generate you by default, and then you can change some parameters and put it back here. Yeah.
I want to ask for your example where you use restraints for the water molecule. For the calculation of the PMF, do you have to take into account the harmonic restraint that you put in the water molecule, or can you ignore it and just... Okay.
No, in that case, for the restraint for the water molecule, I did not put. I just need that restraint. It's very low restraint. I mean, it's just a very small force, just to keep that water molecule in the QM system, and so it will not flip out of the QM box. Yeah. But for the umbrella sampling, you also put that harmonic restraint on your reaction coordinate, and this is.
So does the So the restraints for the reaction coordinates are the only ones you put into the WAM calculation?
Into the process application.
Okay, thank you.
I have a question regarding the boundary. So when you disrupt the bond between the QM and MM system, like at the boundary, and let's say if the atoms are not only carbon-carbon but carbon-oxygen, and you replace that bond with the hydrogen, simplest atom,
Yes.
then the molecular orbital overlap is not similar to the
Yes.
real situation.
Yes.
So how do you handle this?
Yes, so rule of thumb, do not try to cut your QM, do not try to cut your QM system on the polarized group, on the along the pi systems, and along something else I forgot. But idea is that the best bonds when you should cut between QM and MM system should be, the best case scenario is sp3 bonds between two carbon atoms. So please choose this. Usually if you have proteins, the best bond where you could cut is, yeah. So for the protein, it's very well defined usually, because the protein you have this peptide bond, yeah, and then you have this C alpha atom to which you have this your peptide groups, protein groups, amino acid groups is applied, yeah, and you have this peptide bond. Remember, peptide bond is a pi system. Do not cut here. So this cut is not viable. So the only thing where you can safely cut is this bond between C alpha, this bond, or this bond. Typically, that's where you cut in the proteins. Yeah. So please do not cut the peptide bond. Yeah. And yeah, the rule of thumb, try to cut them between the sp3 atom, or at least between sp3 and sp2 atom, like here. So here you have sp2, sp3 cut. Here, still possible. But do not cut between two sp2 atoms, like here. Yeah.
And how do you decide the boundary? How large should be the boundary for QM and MM? How to decide the boundary for the QM system?
The box?
Box size, yeah.
Okay, again, the best approach, and that's what the implemented in the interface, is that your QM box should be 50% bigger than the linear dimensions of your QM system. So if you have, for example, I don't know, take the largest distance in your QM part, for example this one, and make the total box at least 50% bigger than this largest size of your system. Of course, if your system is big enough, your box will become unusable anymore. It will be too big. So that's why I suggest what you can do. So this is the best case scenario, like 50% bigger than the QM size of your QM system. But usually it is fine if your box will be, let's say, 2 to 3 angstroms bigger than the size of your QM box, largest size of your QM box. Yeah. Let's say if your largest distance between your two QM atoms is 1 nanometer, yeah, like 10 angstroms, then the box of 13 to 13 to 13 angstroms will be enough usually.
How does the QM system is fall under the PBC condition, like periodic boundary condition? When you for the PBC system, when you kind of replicate the system in the 3D boundary. So how does it how does the molecule that enters into one end replicate the other system?
This one?
Yeah, here.
So it's replicated like this. So you so the quick step, so itself, it can only calculate these QM boxes. It doesn't know anything about the MM box. What it do, so it first wraps the potential of MM atoms onto the QM system box. Then it calculates this periodic boundary conditions of this QM system. So it will be just 3-dimensional cube of these QM systems, yeah, in all dimensions, replicate in all dimensions. And that's what quick step will do for you. And then as an additional step to recover back the correct periodicity, because QM box is usually much smaller than your MM box, yeah? So it just does this decoupling recoupling scheme of the black hole. And what it is doing, it is try to calculate the energy just of this one cube of the system by using decoupling. So it decouples via this multiple expansion of your electron density. It's really a huge mathematical thing. So it's described in this paper, so you can look at it and see how it's doing. But it's a lot of equations here involved, which is not part of this talk at any point. But the idea is that you try to recover first what will be the energy of this single QM box without these boxes, and then put back them with the correct periodicity, so that your QM box here, QM box there, and recalculate back the interaction energy between them. And then it will be a correct energy and gradients with respect to periodicity. Yeah. That's why usually, actually, it's very important here. That's why your QM system, QM box size should be bigger than your QM system. Because in reality, if your, so it should be somewhere here, yeah? So, because if your QM system will cross this boundary, then the decoupling recoupling will fail. Because it's already in the next box. Part of your QM system will appear in the next QM box. It's not a problem for general CP2K in case, for example, of these metal systems or whatever. It happens here and there. But for biological system, it is important, unfortunately. Yeah. So please always keep such that your QM system are fully inside the QM box first. And it is does not touching the boundaries of your QM box, so that it is very well in your size of your QM systems is such that it can be fit fully into your QM box, yeah, with some additional space at the end. The CP2K will do recentering of this QM part in the QM box at each step anyway, so that's not a problem. The only thing you need to take into account that if you are using your own CP2K input in the GROMACS, not the pre-generated one, then you need to be sure that your QM system is located at the. Yes, I need to draw it back. So basically, this is your coordinate system, yeah, x, y, z. So the thing is on this 0 point, and the GROMACS considers that your box are going. I guess this, maybe not, okay. But box is like this. So it's located, it goes into the positive direction from 0 point. So this is one of the, how it's called. It's not the center of box, it's one of the vertices of the box, and it goes into a positive direction. CP2K use the same scheme. Your QM box is located here actually, always. Because CP2K considers it like this. It tries to shift it to that point. So this is your QM system, yeah. And if you are if you are doing this automatic generation, then the GROMACS will calculate this translation such that your QM system will appear in that QM box. But if you are using your own CP2K input, then you have your own QM box. Be sure that the initial coordinates, which are passed to GROMACS in GRO file or with a conv GRO or whatever, that it made such that your QM system is centered inside QM box which you defined in your CP2K input file, yeah, and it should be really near the from 0, 0, 0, 0 point towards the positive direction, your QM box, yeah. Okay, so for hands-on session, I will just quickly show you what you expect to have in that tutorial, because there will be like 3 systems and 4 tasks in total. So I think the access to the cluster will be not just for these 2 hours, but for longer. So you can, if you don't manage to do anything in time, you can do it later. So idea would be to show some options which you can use with the GROMACS CP2K interface and how to use it. So we will start with a simple setting up the simple QMM calculation, just pure, in reality this is pure QM calculation. Yeah? So we just take a very small system, which is N-methyl acetamide, a very simple example of this peptide bond, actually. And there will be no MM system, zero charge multiplicity, and we just try to do some simulations with it. No reactions, no anything, just minimization and NVT simulation. Temperature coupling. So this is the MDP parameters which you need to look at. So basically, this is more or less standard GROMACS input parameters for energy minimization, but with adding this QM section. Okay, so this explanation of what you expect to have in the CP2K input files with grid cutoff. So as I said, so the grid cutoffs and everything is set to kind of high numbers for stability mostly. Okay. Yes. So system elements. Okay, so first you will perform the energy minimization. Second, you will perform here the NVT simulation. Second task will be about the umbrella sampling, how to do it in GROMACS. So we will take again the simple system, which is just steel band molecule, and we will try to do that isomerization of it over this bond, which is shown in the slide. Yeah, that's already shown in the main presentation. So the idea of umbrella sampling. So here is the explanation of how it's done in GROMACS. So in GROMACS, you need to use pooling code for this. So it is in the MDP file you have this pool and coordinates in groups, and how to define this dihedral angle. It is through the 4 groups, which each of them is connecting the to. In that case, it will be first group is they are shown here. Yeah. So the first group is this ring, the second group is this atom, third group is this atom, and fourth group is this second ring. And then the pooling is done along the dihedral, which is connecting this one with this one, and then the second dihedral is this one with this one. So it's defined by the 3 vectors, basically. So this defines 3 vectors between 2 groups. Then you would need to put your own coordinate here, and yeah, just do pooling. So, and this again QMM parameters to put. And what you expect to do, so in the end simulation, it will not in your case look like this, because this is just pooling along the coordinate. You will do it umbrella sampling, so meaning that you will, in each of the points, you will do like 100 steps. And then this example, what will happen if you do this on the pure MM classical level, this reaction, and this have a huge barrier. So, okay, this explanation how the GMX ham working. But this what you that's what you will get after your simulations. So the problem would be that there will be a dip here. Usually when you see that in the PE, the umbrella sampling simulations, meaning that at these points you don't have enough sampling. Yeah, and if you look into the histogram of this, in each of the umbrellas, you will see that indeed there is no points here. That's why it just dropped here to 0. So to get it better, you would need to increase sampling to 10,000 steps, but it would take, of course, much more time. It will take approximately 1 day, something like this. So we will not do that, but there is example what will happen if you can do this. Yeah, and there is a how it's called comparison of the MM isomerization with MM force field, which is artificially high barrier, and these QM methods. So QM low means here that is only 100 steps for each umbrella window, and this is 10,000 steps for each umbrella window, which is already converging more or less to the correct number. And the last 2 tasks will be about setting up the protein systems, real protein systems. And for that, I've used the GFP protein. And later in the task number 3, GFP protein, and the task number 4, it is calculation of spectra, excitation spectra of this protein, UEVs, excitation spectra with TDDFT. So, and for this, we will use the following setup. So we will take the chromophore from the PDB file, from the protein database. We set up first initially the classical simulations, and then we'll switch to QMMM. And in the task number 4, we'll calculate the spectra of it. Okay. So that's how you need to define this. To calculate the spectra, of course, you need to define your own CP2K input, where you ask the CP2K also to calculate the TD-DFT spectra in each point of MD simulation. And this is done using this QM method input. And if you use QM method input, then in the GROM-PP, you should add additional minus QME option with CP2K input file. You need to provide your own CP2K input file. Okay. So, and how to do this in CP2K, you just add additional section which is called properties, and here you just calculate 5 states with TD-DFT. Here. Okay. And the output in the CP2K will look like this. So it's excitation energy, oscillator strength, and transition dipoles. From that, we would need only this and this. So these 2 columns. And then we'll gather the trajectory. So gather them over the trajectory and convolve with Gaussian functions into something like this. Again, with increased sampling, the spectra looks much nicer than with a low number of points, let's say. Okay, some additional options which you can explore yourself. And yeah, I will probably show you now how to work with the tutorial. Yeah, it would be nice. So let me open it, something like this. Yeah. Okay, so let's go to this Jupyter Hub. Okay, I'll stop server, so it will not interfere with this. Okay, so you need to. Okay, you need to start the server again. Choose a preset. Okay, there should be this kind of directory which is called GROMACS, CP2K-GROMACS, which have these exercises day 2. Yeah. So, but what we want to go here, what you need to do from here first, please download this handbook. It's PDF file. I think you first can open it in your browser if it can, but you can also download it here. And just open. Yeah. So there is a step-by-step instruction what you need to do for each exercise. Also some useful commands. So how to go to the terminal and where you can use PyMol or VMD for drawing your system. It's go to the 6Pro desktop from the Jupyter Hub. Yes, so it will appear terminal here, from which you need to go to that directory first. Yes, go to that directory first. And then from here you can start all the tutorials from the handbook. So, because here you need to go to the directory, open Xpro desktop, and then go to these exercises day 2. Okay, and from day 2 you can then proceed to the exercises. Yep. So any questions? How to start? No, if no, you can then proceed with the hands-on. If you have any problem or question, just please call me or Xin or someone to resolve your problem. Yeah.
Question. Should the potentials, like the pseudo potentials, should be in the same directory?
The pseudo potentials and basis sets. So typically, when you compile your CP2K, it will preset the directory with the data with all that basis to your. It will build into. But if not, you can also specify the location of them. They either need to be in that precompiled directory, or in the directory with your simulation, or in the directory which is defined by the environmental variable CP2K data dir, or CP2K data, I guess it's called.